In this video, I will be discussing a concept known as the Fourier Transform, specifically its uses in computed tomography, or CT medical reconstruction imaging. First, how does medical reconstruction imaging work? Well, an X-ray machine sends electromagnetic waves through an object. The intensity of these waves is then detected on the sensors located below the object. A CT scan, on the other hand, works by rotating an X-ray machine around an object. Soft tissues such as muscles block fewer rays, leading to greater intensity readings, while harder tissues such as bones lead to lower intensity readings. Unlike an X-ray, a CT scan has the capability of gathering and compiling 360-degree views of a targeted area. The Fourier transform is what allows computers to turn this list of light intensities into a 3D image. The basic principles of the Fourier transform have been around for thousands of years. Babylonian mathematicians used a primitive form of harmonic series to calculate astronomical positions, and the ancient Greeks studied systems of astronomy related to the Fourier series. Variants of the Fourier transform were used by Alexis Clairaut in 1754 to compute an orbit using cosines, and in 1759, Italian mathematician Joseph Lagrange computed coefficients of a sine series for a vibrating string. It wasn't until 1807, however, when Joseph Fourier published his bold claim that any random function could be represented as the Fourier series. Although Fourier got the credit, some historians are divided as to how much Lagrange and other mathematicians were responsible for Fourier's theory. Today, the Fourier transform is an extremely powerful mathematical tool that has applications in nearly every field of engineering and physical science. In fact, the Fourier transform was one of the first tasks given to early computers in the 1960s. In its most basic form, the Fourier transform breaks down a given waveform, whether it be a function of time, space, or some other variable, into sinusoids, which is just a fancy word for sine and cosine waves. Abstractly, imagine that the original function is a smoothie. The smoothie itself is composed of multiple ingredients: strawberries, blueberries, banana ice, and whatever else you like. If you blend the ingredients together, you get a smoothie, or a function. If you filter out the smoothie, you can find its individual ingredients, the ingredients being sinusoidal functions. Why sinusoids? Well, when we break down a function, we want the parts to be easier to work with than the original function. Sinusoids are nice functions to work with because they are infinitely differentiable and because they don't change shape when we transform them between the Fourier and inverse Fourier transformation. This is only true of sinusoidal functions and not other functions. A transform is a mapping between two different sets of data or domains. It can change information in the time domain, for instance, into information in the frequency domain. Rather than thinking of the Fourier transformation as a single equation, the concept should be thought of as two functions that are inverses of one another. Unlike Fourier's earlier Fourier series, the Fourier transform can be used over negative infinity to infinity. Fourier and other mathematicians found that any function in the time domain can be described by a sum of sinusoids, and these sinusoids in turn can be described by their frequency, their amplitude, and their phase. All of these components tell us what we need to know to describe the signal. We can plot the amplitude and phase at every frequency. Most signals are not only one sinusoid, but multiple sinusoids at different amplitudes and phases across the entire spectrum. CT scans take projections from many different angles and produce 2D slices, sort of like the pictures that come from a camera. The Fourier transform is a trick that allows you to take measurements as a function of angles and invert the data into pixels. If f of xy is the original image, and a projection is taken of that image at angle theta, we can denote the projection as p theta r. Next, a 1D Fourier transform of that image will produce a slice image of the object that looks something like this. Taking a 2D Fourier transform of the image produces an image in the frequency domain that looks something like this. The central slice theorem, which is crucial to our understanding of the Fourier transform, tells us that the 1D Fourier transform of the projection of an image is the exact same as the values of the 2D Fourier transform of the object along a line drawn through the center of the 2D Fourier transform plane. The Fourier transform allows us to take these image slices to build up a 3D image of whatever object the CT scan is measuring, using an integral. From CT scans to earthquake waves, the Fourier transform allows us to better understand a function by transforming it into easier to understand parts. It will continue to be a crucial concept in mathematics and science for years to come.